Hi class, welcome back to lectures on quantum field theory, and this is now chapter 9 on spontaneous symmetry breaking and Higgs mechanism, and this is the first part of the lecture. So if you could recall, Noether's theorem relates conservation laws to symmetries in the Lagrangian. So I think you'd go back to the third chapter of this series of lectures, so you will be able to review Noether's theorem. So when a quantum theory is invoked, these symmetries can take the form of invariance under unitary transformation. Say for example, the U1 symmetry, which means that a Lagrangian L, which is of course a function of the field and the derivative of the field, is invariant under this transformation. So it's just a shift in the phase of the field. So when theta is not dependent on the space-time coordinate x, then we have a global symmetry. In quantum field theory, global symmetries represent something that cannot be measured, like the phase of a wave function in quantum mechanics. So in that case, the wave function psi xt could give the same predictions as exponential to the I alpha times psi xt. So it's just the phase that changed, not really on the wave function. But if your theta depends on the space-time, that means your theta is now a function of x here, or space-time, then you have a local symmetry. In that case, local symmetries are important in speaking of relativity, because they represent the physical fact that quantities are conserved locally, like charges or lepton numbers or any quantum number. A local symmetry preserves causality as required by special relativity. This means that the cause of something that happens in this environment must also happen within the environment. Say for example, if you have a charge here on Earth and you lose some charge, it doesn't if you have the charge appearing on the moon, it's not anymore local invariance. So in that case, if you have a charge passing through a wire in this, for example, in this environment or in this space, then a charge passing through a wire, the amount of charge that goes in at one end of the wire must come out at the other side of the wire. So that's it for local symmetries. Local and global U1 transformations can be distinguished. Say for example, you're studying complex variables. The exponential e to the I theta is a point on a circle, a unit circle, a circle with radius 1. So any point in a circle can be represented by a vector, which is an arrow from the origin to that point in the unit circle. So for a global transformation, the theta there would be constant, so that your e to the I theta is fixed in value throughout space-time. Hence you call that global. On the other hand, if your theta is not constant in space-time, then the e to the I theta would have different values depending upon the location of theta x in the unit circle, and you have different values at different points on the unit circle. So here, if you look at the figure, you have two cases here. So if you take a look at this figure, on the right side of it you have arrows pointing in the same direction, and on the other side, on my right side, you have arrows pointing in different directions at different points in that particular space. So the left side is a global transformation where the value of your theta is constant everywhere, while for a local transformation, the value of the I theta depends upon the space-time location. See, for example, you have here the arrow at this particular space-time point is different from the direction of the arrow at this particular space-time point, and anywhere they really depend on the position, I mean the space-time position. There are also complicated unitary transformations such as SU2 in quantum field theory, but we'd rather discuss this in the electroweak theory. And also it is possible to have Lagrangians that are invariant under other types of transformations, such as this one here. This one introduces the concept of spontaneous symmetry breaking. So here, as an example, we'll consider a Lagrangian that is so-called the phi-4th theory, or phi to the 4th theory, under the invariant, whose invariance is under this one here. So let's do this. So consider a Lagrangian which is of this form. You have derivative of the fields times the derivative of the field as well, minus the mass square times the field square plus alpha times the field to the 4th. So you can see from this Lagrangian that the phi, or the field phi, appears in terms of even powers and derivatives. So in this case, the transformation is unchanged. By the way, this Lagrangian is very interesting. In most cases, if not all, a system that has some symmetry that exists in the Lagrangian may have a ground state or vacuum state that does not satisfy the same symmetry. So we'll investigate more about this Lagrangian and find out if we would be able to find a vacuum state, even if the symmetry is not broken, or could we find some vacuum states when the symmetry is broken, or how do we differentiate them? So if it has a ground state that does not satisfy the same symmetry, then the system has undergone spontaneous symmetry breaking. Now consider a bowl placed upside down, a steel bowl placed on a flat ground, then place a marble on top of the bowl right at the center. This system is symmetric because at the top of the bowl you have a marble, and the marble sees that at every direction that it goes down to is symmetric. The system is symmetric, but the system is also unstable. So if the marble starts out at rest, a slight perturbation will send it rolling down the bowl to the ground. Now, if the marble is perturbed and rolls off the bowl, it will roll only in one particular direction and will come to rest below on the flat ground. In short, you have spontaneously broken the symmetry that existed before the marble rolled down. So the marble now has arrived in a state of minimum potential energy, but it's a consequence of broken symmetry. In other words, the marble was not really on the ground state when it was resting on the top of the bowl. The true ground state of potential energy exists when the symmetry is broken and the marble finds itself resting on the ground. Below. By the way, oftenly in quantum field theory, it can be seen that the vacuum state, that is, an apparent ground state, leads to a true ground state or vacuum state of lower energy if symmetry is broken, or by breaking the symmetry. So vacuum is the state with no fields, that is, your phi is equal to 0, and by calculations through perturbation theory, we can expand about phi equals 0, and then you can view the field as fluctuations about that ground state, and we think of the phi equal to 0 as the minimum potential energy. But when you have a different Lagrangian, like equation 9.2, it turns out that the state with phi equals 0 is not always the minimum, because the true minimum comes out when the symmetry is broken. If you could recall, the Lagrangian is always the difference between kinetic energy and potential energy. And of course, in quantum field theory, your kinetic part or kinetic term would consist of this, and your potential will be some functions of the field or in general some functions of the field and its derivative. But for simplicity's sake, we can just assume that it's a function of the field. So to find the minimum, use ordinary calculus. That is to seek the minimum by computing the derivative of the potential. And that is this one here. And now we're going to discuss an example to find a minimum of a particular Lagrangian. Say, for example, the phi to the fourth theory. Consider the Lagrangian for the phi to the fourth theory, where phi is a real scalar field. So this is your Lagrangian now, and you have different terms here. The kinetic term, you have the mass term where m appears, and of course you have an interaction term. So describe the minimum of potential energy when m square is greater than 0 and m square is less than 0. The kinetic term in the Lagrangian is of course this one, which is just this one, and you have the potential is of course the rest of the Lagrangian here, which is just this one here. So if we take the derivative of v with respect to the field phi, then we'll be able to get this one here. And then what happens is that we will equate this to 0 to get the minimum. So obtain the minima by setting this expression equal to 0. And one extremum would always give you phi equals 0, and that case corresponds to the case where m squared is greater than 0. That represents a scalar field of mass m. By the way, the phi to the fourth term here is, as I've said, it's a self-interactions term, and it has a coupling strength of lambda in this case. So the potential for the Lagrangian in equation 9.4, one of them is phi is equal to 0, which is located here and here, located there. Now, when the ground state is at phi equal to 0, it satisfies the symmetry that is present in the Lagrangian. And of course, the transformation phi going to negative phi is very trivial in this case, because you have even powers of even powers of phi and even powers of derivative of phi. Now, how about considering this other term? We equate that to 0. After this, equating to 0 as well. So it gives us this expression here, and we'll be able to get a field that is not 0 here. So in this case, this is only valid when m square is less than 0 because of the sign here. This situation in our analogy previously corresponds to the ball sitting on top of the bowl, where you have a symmetry when the ball was still at the top of the bowl, or the marble was still on the top of the bowl, and when it went down, the symmetry was broken. It's not anymore symmetric, but it's at the minimum already. So notice that phi equals 0 corresponds to the unstable point where the marble is resting on the top of the bowl. In the case of our Lagrangian, the ball can go from one to another minimum point. You have two choices of minimum points. You have positive V and negative V. Actually, this is nu, positive nu and negative nu. But yeah, here, by the way, nu in this case is square root of negative m square over lambda. So we could choose whether the ball would go to positive nu or negative nu. So only one point, only one minimum can be chosen by the ball, or where the ball goes. It cannot be in two minima. So choosing one of the other, choosing one minimum over the other, breaks the symmetry. So this is analogous to the marble rolling down the bowl and coming to rest at some particular point on the ground. So in this case, you have two minima. By the way, this kind of figure is called the Mexican hat. Mexican hat plot. The potential for the Lagrangian given in equation 9.4 when m square is less than 0. So you can see that it's so different from here. Here you only have one minimum, and you have here multiple minima. So in the case of the Lagrangian, the true minimum are found at either phi equals positive negative nu. The point phi equals 0 is an unstable point, therefore a perturbative expansion about this point will not converge. However, as in contrast, a perturbative expansion about one of the minimum, about one of the non-zero minima, will converge, and this allows calculations using Feynman rules. However, in this case, the symmetry has already been broken, and that broken symmetry actually implied or is the cause of two ground states. This one and this one. By the way, spontaneous symmetry breaking physically leads to the mass terms in the Lagrangian. If you recall the Klein-Gordon equation, this is the Lagrangian for the Klein-Gordon equation. You have the kinetic term in this case, and then you have mass term where m squared is present. So looking at the Lagrangian, you have the mass term here in this given here in this term. So that is the mass of the associated particle of the field phi. So this is very important. A mass term in the Lagrangian is one that is quadratic in the fields, which is a term of the form alpha square phi square for some alpha. Note that identifying mass terms in a Lagrangian by inspection is not always possible. You have to do some expansion or do some algebra trick. Many of the Lagrangians have mass terms that are hidden. Only you can see them by expanding the terms. Say for example in this fictitious Lagrangian given by equation 9.6, you have this one here. You have a kinetic term and then you have another term there in the form of a natural logarithm. So will we be able to find a mass in this case? No, because we don't see anything that is quadratic in the fields, and of course in this form for some alpha, but here you have a natural logarithm. So by inspection there is no terms that are quadratic in the field, so a conclusion might be drawn that the mass of the phi here is 0, but we can actually expand the natural logarithm and we'll be able to find a quadratic term, a term quadratic to the field. So by the way, for a field with 0 mass, you have a field that's representing a photon. So we will expand the Lagrangian in a series. We need to expand the logarithmic term. So look at this. We have the expansion of 1 over 1 minus alpha x is just equal to 1 plus alpha x plus alpha x square plus alpha x cube and so on for alpha x less than 1. This is known expansion. So to introduce the logarithm, we integrate this term, and the integral of that will just be ln of 1 minus ax. And of course you have to integrate each of the term as well here, and that would give you this one here. Where the negative alpha here came from the integral of this one. So you will have ln as this one here, and then you can put this term as a replacement to this one, and then you'll have all of these terms. And so you can find in the third term a quadratic term to the field, and also since this is negative signed, then that the alpha square means it is greater than 0, and this describes a particle with mass alpha equals m, or mass equal to alpha. So the mass term has been distinguished by the original representation of the Lagrangian given in equation 9.6. So again, if it's not obvious, then expand the potential in a series and look for terms that are quadratic in the fields. In this case. So there are also other Lagrangians which we can also evaluate the mass of the particles. So we take two Lagrangians. In this case, you have L1 1/2, you have a kinetic term minus exponential alpha cube phi cube, and then the other one is 1/2 derivative of phi square minus e to the alpha phi. For the first one, by the way, you can expand exponential like this, and so for exponential of lambda phi cube, you could expand that as this one. But in this case, you cannot see a term that involves a quadratic in the field. So you have L1 as a Lagrangian with a massless field. In the case of L2, you have here only exponential of alpha phi, which can be expanded to this one here. And in this case, you have a field that is quadratic, and you can find it, and it's very obvious in here that you have a field with mass alpha. If you compare it with the Klein-Gordon equation. Before we go further, let me just give you some notes on the units. So if you go back to the Klein-Gordon equation and you put all the h bars and the speed of light c back in the equation, you'll be able to see this one here. So if we go back to the Lagrangian, we have to look for the terms that are like this. But in this case, your alpha equated to m earlier is actually equal to your alpha square, equal to m square c square over h bar square. So your alpha is really equal to this, not just m. So therefore, your mass is equal to h bar alpha over c, where your alpha is a unitless number and m will have the dimensions of mass inherited from the values used for h bar, reduced Planck's constant, and the speed of light c. And also, if the quadratic term in the Lagrangian is missing, the 1/2 scale factor, that is, if it contains only a term alpha square phi square, then you have to account for the missing 1/2 if you compare it with the Klein-Gordon equation to get the mass. So in that case, you also have, you just equate alpha square to 1/2 m square c square over h bar square, which is this one. And then of course the mass of the particle would be given by this. Now we would go to spontaneous symmetry breaking and the mass. So we will reconsider again the phi to the fourth theory. So we have a Lagrangian used in the previous example, given by this. And we have found out that the true ground state are given also by this one, given by positive negative nu. So of course it's very trivial if you use phi equals 0, but we'd have to use this one here. Now we have to choose only one minimum. Say for example phi equals nu, and of course if we use that, we have to rescale the field to represent this. We have your field now written to be like this. It's now fluctuating at the near around the minimum nu. So you will have your phi x equal to nu plus some fluctuating function also. So the field is written as fluctuations described by, this is not n, this is eta of x, about the right hand minimum nu, positive nu. So we will now rewrite the Lagrangian in terms of the new field eta that fluctuates about the minimum nu. So the kinetic energy term, we just get the derivative of the field phi, and of course the derivative of nu would just be 0, so your derivative of phi x would just be your derivative of eta x. And if you square that, this equation 9.9, it will also give you this term here. So this one is just a constant. This one are functions eta. So if you also take the fourth power of the field, then you would also have a term that, or an expression that contains 6 terms here. Now we put the terms together and our Lagrangian becomes this very big one here. A long one here. This one is a constant. This one is also a constant. We can drop all the constants because they doesn't contribute. They don't contribute to the field equations for the system. So if you go to the first term in the potential, you can write it as here, 1/2 m squared nu square plus 2 nu eta plus eta square. Then you can write that as this one. If you use m square equals negative lambda nu square, as we used previously in here. Here. So we'd like to drop constant term as well, so that we're left with so in this case you have this one, and this one of course can be dropped, and this can also be dropped. So what happens? You have only this term. If you convert, if you use this expression to convert m, so you will have only this term, and this one is just this one here, and then of course you have to drop this as well, and then you have 1/4 lambda multiplied to this one, and then you have this one for here, and then you have also this one for here, and for this one is here. So as you can see, you also have you can also cancel this one, these two, and then you can also combine this and this one. You can combine them, and then you also have this surviving term, and also this one is it survives as well. So finally you have only these terms, this one, also this one here, and this one here. So by the way, this term here is a self-interactions term, and that is represented by a Feynman diagram that is like a branch of 3 legs with coupling constant lambda. So the other one here, this one is also a self-interactions term, and the Feynman diagram is given by this. You have 4 legs, or 4 legged vertex in a Feynman diagram. Now, can we find a term that is quadratic in the fields? Yes, we can find it, and it's this one. So we can calculate the mass. In that case, the mass is equal to square root of 2 lambda nu. in that case if you compare it with the Klein-Gordon type Lagrangian. So there is a missing one half. There's a missing one half here, so you have to account for that. So you have here in this Lagrangian a kinetic part, the mass term part, and three-legged interactions, and then a four-legged self-interaction. Three-legged self-interaction. So what do we have here? So we have a Lagrangian that has a non-zero minimum because of broken symmetry, or the spontaneous breaking of symmetry. And then we were also able to find the mass term of the field eta. So in the next part of the lecture, we'll be discussing about Lagrangians with multiple particles.